Dear students, in the previous lecture, we had seen a couple of content-based techniques, namely TF-IDF and vector space model and the combinations thereof. Today, I'm going to take a new technique, but before that, let me clarify one thing. When we have already done stop word removal, and then we do TF-IDF also, right? So the point that I want you to think about is whether both these steps, stop word removal as well as TF-IDF, both are necessary or anyone could have done it. For example, if we have not done stop word removal and then we just do TF-IDF, that should suffice. See, in stop removal, we were removing the articles like a and the, for, which are very frequent, right? And they will be frequent across all the documents. So when we do IDF, log row by row W, let me take you, log row by row W, then row will be equal to row 2. Every document will have the, so their importance will be reduced. In fact, that will become 0. So why do stop word removal when we are doing IDF, or vice versa? If we are doing a stop word removal, why do IDF? So let me clarify on this. See, IDF is a computationally expensive process, costly process. Why? Because we have to find out log row by row W. Okay, if you don't do stop word removal, IDF will take care of removing these stop words. But then why do something at a greater cost if you could have done on a smaller cost and a lesser? Okay, so why do things at a greater cost if it can be done on a lesser computational cost? So it makes more sense to do the stop word removal even if you have to do IDF later. Now again, when we have done stop word removal, why do IDF? That is the other part. The reason is that there may be some words which are not necessarily stop words, but still you want to do away with them. For example, the word computer. There is a corpus on computer, and you don't want to see computer as the index word because it is there in any document anyway. So even if you have not done the stop word removal and you haven't removed computer as a word, still IDF should strip off computer because it is homogeneously frequent across the collection of documents. Okay, so that is the point I wanted to make, that stop word removal and IDF both are necessary. Right? You have to take both these steps for the reasons I've explained just now. Now, moving on to the third technique, which is Boolean similarity measure. This is the third. After TF-IDF, after vector space model, this is the third technique, Boolean similarity measures. The need for this content-based technique arises because in the advanced queries, we have combination of words and or even not logical connectives. Even if you go to the advanced queries of Google, you will see its problem. For example, I'm looking for documents containing analog computing. So I essentially mean that I'm looking for the documents which contain analog and computing. It should contain analog as well as computing. Right? Now, there may be a scenario where when I launch the search for analog computing, I also got the documents which contain analog and computing and also contain digital. But I don't want to see digital documents at all. So in that case, what I'll do, analog and computing and digital bar, which means I want to see the documents which contains analog and computing, but no digital, right? So that way you can have complex and or queries, just as the Boolean expressions we have. Now, if we have such a complex Boolean query, how do we compare it with the documents in a corpus and select the documents. So essentially, it all boils down to finding out the similarity between two Boolean expressions. One Boolean expression could be the query, the other Boolean expression could be the document. Right? For example, there are 10 documents in a corpus, so I'll take all the keywords. After stop word removal stemming, I'll join them using AND connective for a document, and then OR and connectives for all the remaining document, for the second document, or the keywords of the third document joined using logical connective and so on. So essentially, it is comparing two Boolean expressions for their similarity. So that is why I've written Boolean similarity measure for, let me see, Boolean similarity measure for computing the similarities of one document to another and documents to queries. Right? Much the same way as we have seen before, R1 to R2 or Q to R1, right? Or R1, R2, one of them may be query, the other may be a document and so on. So phi Q and phi R are the sets of documents in the response to query Q and in the cluster R of documents. The first and the foremost is the Jacquard's coefficient. Similarity between the query and the resource is the documents that are common in Q and R, the keywords that are common in Q and R, the number of documents that are common to Q and R, and the union, right? And then we take the cardinalities. However, I need not pay more time to it because this is not a very useful similarity measure. Why? Because this measure requires the actual results to the query. Right, so it may be useful as an index of comparison, but it is not useful as a similarity measure as such, because you actually need to retrieve the documents and then count how many pertaining to query, how many pertaining to resource, finding out their intersection, dividing it by the number of the union documents. So it is not of much use. It is more of useful as an index of comparison and more of a theoretical interest. Let me move on to a practical Boolean similarity measure, right? This is attributed to Radke measure. The Boolean expression is transformed into reduced disjunctive normal form, which we normally call a sum of product form, a disjunction or of a list of reduced atomic descriptors, right? So I'll explain through examples. The Radke measure, I've put this star in order to differentiate with the Jacquard's coefficient. So S star between QR is the number of, if you remember, we'll have to recall what all we studied in digital logic theory course. So what all are the minterms that are common divided by the union of minterms? That is what it means. TQ union TR and intersection resource TQ union TR, right? And this is the union. Let me take an example. Things will become more clear. But we'll have to put it in the canonical sum of product form, right? This sum of product form has to be canonical sum of product form. We'll see what is the problem with that later. Let me take the example first. Suppose I have a query, a Boolean query and a Boolean resource. Now my problem is to find out the expression between these, the similarity between these two Boolean expressions. The RDNFs, which means the canonical sum of product form of Q and R, you all know can be done using T1 and T2 and T3, or you know how to do it, right? First of all, we'll have to do T1 and T3 or T2 and T3, and then for the canonical form, I should have all three terms in it, right? So this one can be, Q can be converted into the canonical sum of product form like this. And R, for R, T1 and T3, okay, I know that I'll have to multiply with T2, right? And T bar, right? T2 or T2 bar. This you all know, this is OR and this is AND, right? This is and this is the symbol for OR. So in order to convert it to the canonical form, I'll have to multiply it. So T1, T2, T3, see T1, T2, T3 or T1, T2 bar or T3. This is another way of representing a negative expression. So now this expression says that you have to find out the number of terms that are common in both. So you see this one and this one is common. Likewise, this one and this one is common. So in the numerator, I'll have 2. Intersection, right? Intersection. So I'll have 2 terms. Whereas when I find out the union, then I'll have 3 terms. So the similarity between the query and the resource is 2 upon 3, the intersection, the number of terms that are intersection and the number of terms that are in the union. So 2 by 3, which is 0.667. I'll take more examples later. Okay, let me take the example first. For the Radeke method, I'll take the example and then I'll come back again. Find out the similarity between resources R1, which is AB or A dash D, and R2 is equal to A dash B plus A. So I'll find out the similarity between these two resources. So first of all, I'll have to convert them into the canonical sum of product form. One way is that you multiply, you AND, use the distributive property AB and C plus C bar plus A bar, C plus C bar D, and then you find out the shortcut way we know is through K-map itself. You all know that, so let me make use of it. Let me first represent R1. R1 as AB. Okay. So R1 as AB will be these two, right? Will be these two. AB, A, and then I have B. So that is why I've written 1, 1, right? And A bar D. So A bar D is these two. So I have again written 1, 1. Right? 1, 1 there. Finally, I down about R2 into the canonical sum of product form. So R2 in the canonical sum of product form is A bar B. So A bar B are these two, right? So I've written 2, 2 because I'm representing R2 and AD. So AD is these two terms. Okay. So I have represented both R1 and R2 in a K-map, which is essentially the canonical sum of product form. Now what remains is to find out the union of terms. Union of terms I can easily see is 6. So I've got 6 here. And the intersection is 2 only. 1, 2, 1, 2. So it is 2. So 2 by 6 is 1 by 3. Right? So you give me any 2 Boolean expressions. I can always convert them into the canonical sum of product form by using either the distributive property or by using K-map itself. Right? And then I find out how many are the min terms that are common and how many min terms are there in the union. Okay, I divide the two and I get the similarity. For example, they had been the same. R1, suppose I want to find out the similarity between R1 and R1 itself. Okay, so if I do it, the union and intersection will exactly be the same. When union and intersection are the same, the similarity will be 1. And suppose I'm trying to find out such terms that are completely, they have nothing in common. The intersection is null. So in that case, the numerator will be 0 and the similarity will be 0. Okay. So the idea in Radeke measure is to convert the given Boolean expression into its canonical sum of product form and then find out how many min terms are common and how many min terms are there in the union. You divide the two and you get the similarity measure. Right? Seems simple. But there is a problem here. The problem is that of converting it into the canonical sum of product form. That is our main problem. So the problem lies in converting the expression into the canonical sum of product form. I remember we have discussed in our second year logic theory course that whenever you have to convert a given sum of product form into the canonical sum of product form, it is NP hard. Why? Because for every term that you have to add, you have to multiply with you have to add it with the term that is to be added and its complement. So for example, we have to do, suppose we have to do something AB, right? And I want to add C. So I'll have to do C plus C bar. If I have to add D also, then D plus D bar. So with just the C, I had to have 2 terms. But with D added, I have to have 4 terms. If I have to add E also, then 8 terms. So see, it is growing exponentially. 2, 4, 8, 16, 32, 64. So the number of terms that are to be added or number of variables that are to be added, it goes 2 to the power those many numbers, the number of variables that are to be added. So converting a given sum of product form Boolean expression into the canonical sum of product form Boolean expression is NP hard, right? So that is what creates the problem. Because, you know, NP hard problem we cannot deal easily, right? So there is the second approach, Lee and Danzig measure. These were the two scientists, computer scientists, Lee and Danzig. They came up with such an expression in which the Boolean expression is transformed into its compact disjunctive normal form, not the reduced, but the compact or of compact atomic descriptors. So in this measure, you just have to have the sum of product form, which may not necessarily be the canonical sum of product form. Just a simple sum of product form would do. So the problem of converting into canonical sum of product form, which was creating the problem by getting into an NP hard mode, that is solved using Lee and Danzig measure, because the expression, similarity expression they have given is requiring just the sum of product form and not necessarily the canonical sum of product form. Now, how does it work? It works on individual product terms, right? The ith product term of Q and the jth product term of R. And it says like this, 1 upon 2 to the power, the number of terms that are there in R but not there in Q, plus 2 to the power, the number of terms that are there in Q minus not there in R. Set subtraction, we know A minus B, there are two sets, A minus B. What does it mean? The number of terms that are there in A but not in B. That is what A minus B set subtraction is. So it is basically set subtraction, n minus 1. And then you take the average of all such combinations. This is basically average. Summation I is equal to 1 to Q, J is equal to 1 to R. You add all of them and divide by Q into R, the number of product terms in Q and product in R. Let me again explain with the help of an example. The same example that we are taken for Radeke measure. Over here, we just have to use these terms as such without being required to convert them into the canonical sum of product form. How can we do that? And also there is one more condition, that if T, R, J and TQ, I, they are null, then their similarity will be 0. That is no term common. Or if there is a positive term here and a negative term in Q, then also it will be 0. Okay. So essentially it will be R and Q should not have complement terms, should not have intersection being null. Then we make use of this expression. So let me move on to the example. This is the first product term of Q and the only product term of R. So, but this is not in sum of product form as yet. So first let us convert it into sum of product form. So how can we do that? T1 and T3 or T2 and T3. So converting into sum of product form is not NP hard. Converting into canonical sum of product form is NP hard. Okay. So we just converted into sum of product form. Now I'll compare this with this. So you see There is no complement term, so that is ruled out. Intersection is also not null, so that is also ruled out. Now I'll apply the expression. How many terms are there in this but not in this? Right? 0. So 1 upon 2 to the power 0, because all the terms that are here are there too. Likewise, all the terms that are here too. Right? So 1 upon 2 to the power 0 plus 2 to the power 0. I'm sorry, this should be minus 1. This should be, because that is what the formula is, minus 1. Right? This is minus 1. Right? So 1 upon 1 plus 1 minus 1 is 1. Makes sense, because they are exactly similar. They are the same, in fact, so it should have been 1. Now let us go on to comparing this with this, the next product term with this product term. When I do this, I see that there is no negative term, so it cannot be 0. The intersection is also not null, so it cannot be 0 either. Now let me apply the formula. Again, it should be minus 1. I'm sorry. So T2, how many terms are here in this but not here? 1. T2 is not, so 1 to the power 1. Plus, how many are here but not here? 1 again, which is T1. So 1 upon 2 to the power 1 plus 2 to the power 1 minus 1. So it becomes 1 upon 3, which is 0.33. Now you take the average of the two. So that will be 0.667. So the overall similarity between Q and R is 0.667. So this Lee and Danzig, I'll take another example. Just hold on. Lee and Danzig measure reduces time and space complexity from exponential to polynomial. Exponential because canonical sum of product form was required. And polynomial because the canonical sum of product form is not required, only the sum of product form will do. Right? So let me take this example, which we've already evaluated using Radecki method. Now we want to do it using Lee and Danzig method. So both R1 and R2 are in the sum of product form already. So we need not even convert them into sum of product form. Leave alone canonical sum of product form, right? So I'll compare this AB with AB. So it is between R11 and R21. The first product term of R1 and the first product term of R2. It is 0 because here we have A and here we have A bar. That is why it is 0, right? Now comparing the first product term of R1 with the second product term of R2, which means AB with AD. AB with AD, their intersection is not null and there is no complement term either. So the formula will apply that we have seen. How many terms are here but not here? 1, which is B. So 1 upon 2 to the power 1. How many terms are here but not there? 1 again, which is D. So 1 upon 2 to the power 1 plus 2 to the power 1 minus 1 is equal to 1 by 3. Right? All right. Right. So it becomes 1 upon 2 to the power 1 plus 2 to the power 1 minus 1, which is 1 by 3. So this is about the similarity of AB with AD. Now I'll take the second term of R1, second product term of R1, which is R12, with the first product term of R2. So essentially AB with A dash D with A dash B. Now here both of them, they are complement, A dash. So it will not be 0. Had it be one of them had been A, the other would have been A dash, then only it would have been 0. If both of them are complement, then it will not be 0, right? And also there is their intersection is also not there. So 0 will not apply. We'll apply the formula instead. So when I apply the formula, 1 upon 2 to the power 1 plus, because D is here but not here, plus 2 to the power 1 because B is here but not here, minus 1, which is 1 by 3, right? And then finally, I have to find out the similarity between A dash D and AD. This will be 0 because we have A dash here and A here. Complement, right? So that will be 0. So now I take the average of all 4, 0 plus 1 by 3 plus 1 by 3 plus 0 divided by 4. That will be the overall similarity between R1 and R2, which is 1 by 6. Right? You might say that, Radke method absolute value was 1/3 similarity, whereas here the similarity value is 1/6. They're not the same. So how can they be comparable? Yes, their absolute values or their magnitudes may not be the same. But then when you do the relative grading, because essentially when we are producing the search results, it is the ranking which is important. The ranked coefficient is not important. Why am I ranking somebody as 1? Why am I ranking somebody as 2? For example, in a class, I'm forming a merit. So 1, 2, 3. That is important for me. Okay. While forming the ranking, it is not important 1, how many marks he or she scored, 2, how many marks he or she scored, 3 marks, 4 marks, 5. That is not important. The relative ranking is important when it comes to drawing the merit. In this web searching also, we have to draw basically the ranks or the merit. We're not interested in what is the magnitude of their performance or their similarity, right? So 1/3 over here and 1/6 over here. That is how we do the Radke method and Lee and Danzig method. Okay. Now quickly, I'll say that we have studied 3 approaches, right? We have studied 3 approaches of content-based techniques, namely TF-IDF, vector space model, and Boolean similarity measure. They're all 3 content-based techniques with the condition that text pre-processing have already been done, which means stop word removal and stemming has already been done. So should they be the ultimate techniques? No. There are a couple of very crucial problems with content-based web search. First of them is search engine persuasion, or which is called keyword spamming or simply spamming. Spamming, we all know, email spam is unwanted email. Similarly, when we have unwanted keywords, that become keyword. The commercial interest of many web page authors to have their pages ranking high for certain queries forces them to do some illegitimate manipulations. These manipulations may go as far as adding text in an invisible ink. When they are writing the page in HTML, they can use the color of the text the same as the color of the background. That way, they can write catchy words like car, maybe repeated many times in an invisible ink. When the user reaches there, he or she finds no anomaly because it's all hidden from the naked eye. But when the web crawler reaches there, I hope you remember what is web crawler. We have seen the block diagram in the beginning. When the web crawler reaches there, it pulls out car 1,000 times. So TF-IDF value goes high. And that page comes top whenever the query for car is launched, even though that page doesn't have any information about cars at all, apart from listing those words 1,000 times. So this is keyword spamming. People hiding catchy keywords on their web pages so that whenever the most searched word is launched, their page comes on top, even though their page does not have relevant information pertaining to that keyword. So that is one problem aspect. The second problem is the keyword we are looking for may not at all appear in a page, which otherwise is very much relevant to the query. For instance, the homepage of IBM not controlled computer. IBM homepage was talking about higher end technologies like RAID, like 5G, like IoT. They found it too trivial to mention the word computer on their homepage. Just as if I'm introducing myself, I'll introduce that I'm Professor such and such. I won't say that I'm a man. I won't say, or I'm a creation. I won't say that. That is thought to be too trivial. So I talk about higher traits. I'm a professor, I'm a PhD, I'm so and so. Nobody introduces himself by saying, मैं एक इंसान हूं, मैं एक आदमी हूं. Nobody says that, right? Likewise, IBM was not putting on their homepage the word computer. But if the word computer is not there, और आपका क्रॉलर पहुंचेगा तो वो कभी भी IBM के पेज को कंप्यूटर कीवर्ड में इंडेक्स नहीं करेगा. So if we rely solely on the content-based techniques, the pointer to the homepage of IBM would not at all be returned in response to a query on computer. these two strange problems. Keyword spamming and absence of keyword, two extremes, but creating very crucial problems, right? So those problems have to be done away with somehow. Okay, so how to remove these problems? In order to remove those problems, we have the power of hyperlink analysis. It comes from the fact that it uses the content of other pages to rank the current page. This gives an unbiased factor to the ranking. So in our next lecture, we will see how can we do away with these couple of problems that are inherently there in the content-based technique. So we will continue from here. Thank you very much.